At the beginning of time and the center of every black hole lies a point of infinite density called a singularity. Physicists still believe that if they can come up with a coherent explanation for what actually happened in and around singularities, Charles Misner of the University of Maryland called it a mixmaster universe after what was then a popular line of kitchen appliances. Einstein's general theory of relativity, which is used to describe the gravity of black Einstein's equation, couldn't be solved analytically, and even with them it was too complicated for the numerical simulations of the time. In the last few years, physicists have been revisiting the chaos around singular. In 1969, on a visit to Moscow, Thorne was given a manuscript by Evgeny Lifshitz, a prominent Ukrainian physicist. Lifshitz had found a new solution to Einstein's equations of gravity near singular. Earlier black hole models assumed perfect symmetries not found in nature. The BKL solution described what might happen in a messy, more realistic situation. The result was not a smooth stretching of space and time inside, but Jerome Misner and the Soviet group had independently alighted on the same ideas using similar assumptions and different techniques. The BKL group used it to solve the biggest unsolved problem of their theory, mathematical relativity. Relativity holds that two regions of space can be disconnected, meaning that nothing that takes place in one region can have any possible effect on the other. But regions of spacetime can also become disconnected or decoupled, and the strong gravitational fields can cause space to decouple. This means that each tiny part of space behaves on its own terms. This makes the math much simpler, though still quite complicated. John Hartnell has been analyzing the chaotic behavior found inside black holes in the hopes of coming up with a quantum theory of gravity. In their account, around each decoupled point, space stretches in a random direction and compresses for decades. Physicists and mathematicians have wanted to show that these chaotic dynamics are not an artifact of the simplifying assumption of decoupling. By the early 2000s, exponentially growing computational power and new algorithms made it possible to perform this. Correspondence is often compared to the way a hologram can make two-dimensional structures appear to be three-dimensional. Gravity only appears on the high-dimensional side of the correspondence, called anti-de Sitter space. Hartnell and his students used correspondence to find out what happens inside an ADS black hole. They found chaos similar to that BKL had earlier discovered. Over the past half-decade, he and his collaborators have continued. All has shown that it arises even in a toy ADS/CFD model where the speed of light is set to 0. Olin said that Henno, among others, had anticipated that this should happen, but that Hartnell and his student Ming Yang tried averaging the many bounces in a black hole. They found a pattern using this technique related to abstract mathematical functions called modular forms. This suggests that a known mathematical language can be used to understand. The Quantum magazine is an editorially independent publication of the Simons Foundation. Its mission is to enhance public understanding of science by covering